All right, so we've been looking at roots of the characteristic equation, especially of second order equations, but these methods work in all orders. We want to see how looking at the roots of these equations helps us determine the general solution of a linear homogeneous equation. So the last case we want to look at is the most complicated, and I'm going to just use some examples to kind of show you how this works. If you want to see more about formally why this is working, you need to do some further study on complex numbers, which you will see in other classes. But for our purposes, we'll just keep it simple here and just use some examples to illustrate why this is going to work. So I want to use two examples. I'm going to start with this first example, just to illustrate that what we would do in general and how it leads to a problem which is different from our other two cases when the roots of the quadratic equation are either two real numbers or one real number repeated. So in this case, we have a characteristic equation, r squared plus 2r plus 10 equals 0. If we plug that into the quadratic formula, we get two roots. We get formulas for two roots, but we notice there's a problem. The problem is we have a negative in the square root. So this is, on the surface, if we don't have any knowledge of complex numbers, which is what we're just going to talk about in a minimal manner. But if you don't have any knowledge of this is a problem because this doesn't tell us anything. It doesn't give us any real numbers to work with. So in this case, we're kind of stuck, and we have to make some other observations to figure out how to use this information. And the point is, these two roots that we have, even though they don't make sense as real numbers, they are going to tell us what to do. So we still want to be able to determine these, and using the quadratic formula is all we need to determine what information we need to construct our solution, our general solution. So that's what we want to talk about next, is how do we use this information. So this example right here is actually a bit complicated. So what we're going to do is we're going to consider a much easier example and then realize from it that what's going to happen is, instead of exponential functions and power functions arising in our solution, when we have complex roots, what are going to pop up are trig functions, sines and cosines. And this has real implications to engineering and various other things, which means that complex numbers, even though they're called imaginary, they actually help us solve realistic problems. So let's consider a simpler example where the first derivative term is zeroed out. And the reason I'm picking this is because it's easy to see what two solutions are. You can easily check that both cosine of 2x and the sine of 2x both solve this differential equation. Just check it on your own. All right, the second derivative of cosine of 2x is going to be a negative 4 times the cosine of 2x. Plug that into the equation, you get 0. Same thing happens with the sine of 2x. So we do know what the general solution of this is just by observation. We know that we found two functions that solve it, so we can construct the general solution from those. But again, the characteristic equation, if we plug it into the quadratic formula, and I've just done that here without simplifying anything, and we're going to get negative values. We simplify this. What we actually have is the first root is a complex number. It's 0, the real number part is 0, plus an imaginary part, 2. 0 plus 2i, or just 2i. And the other one is going to be a minus 2i. And that's plus and minus comes from the quadratic formula. And what is this I? Well, if you haven't really worked with imaginary numbers or complex numbers, it's just an algebraic convention which allows us to notationally simplify square roots of negative numbers. So this number I is called the imaginary unit, or the square root of negative 1, which doesn't exist as a real number, but algebraically it does exist, because by defining it to satisfy the equation I squared equals negative 1, we can rewrite square roots of negative numbers. So again, as I said before, complex numbers or imaginary numbers, the word imaginary is not the best word to be used, because although these numbers do not exist as real numbers on our real number line, they do exist as algebraic numbers, and we can compute with them, and the rules of algebra apply to them, and the answers we get using them do and are consistent with realistic problems. So we do have to deal with these, but in this class, this is at a minimal level. This is really the only case where we have to understand that these numbers exist, and now we're just going to know how to use them. So going back to this simple example, we found by simple observation two solutions, cosine of 2x and sine of 2x. From our knowledge of linear differential equations, we know that we can form the general solution by just combining these two and putting in some constants c1 and c2. So this is the general solution. What we want to observe, though, is the important thing. Remember what the roots of this characteristic equation were. They had this form of some real number plus or minus some real number times I, the imaginary number that's the square root of -1. In our case, these numbers were a equals 0 and b equals 2. Now if we take that and just kind of look at our general solution, we see the number 2 is appearing in our solution inside of the trig functions. And this is what's going to be the general observation, is when we find these complex roots, all we have to look at are the two parts, the a and the b, the real number parts. The a part is going to be part of the solution, and the b part is going to be part of the solution. And what this example illustrates is where that number b gets placed. It gets put into our trig functions. And remember what this is doing. You take a trig function, these are periodic functions. Their graphs are like waves that keep going on, repeating themselves. So when you put in a number like 2 or 3 or 4 or 5 or some bigger number, all that's doing to the graph is it's making the graph oscillate more and more. So we use trig functions, and we put different frequencies, and that's what these numbers are. They're like frequencies to make it a wave that has a higher frequency. And this allows us to analyze things like vibrations, music, anything like that. So trig functions arise when we have things that are oscillating or vibrating. And we'll see later that when we have models of something oscillating, these trig functions will arise in the solutions, and that's why. So the observation I want to make is, what does the a contribute? Well, with more knowledge of complex numbers, this becomes easier to explain, but since this course does not require any formal course in complex numbers or complex variables, we're just going to leave it a simple observation with this example, and then just illustrate that what's happening here in our general solution is once we find these complex roots, the a and the b fall into place. The b determines our trigonometric part, which has the two constants, and then we just multiply each of those by a factor e to the ax. Remember, exponentials have always been arising as part of the solutions when we had a real root, and a is the real part of these roots. So it's somewhat natural to expect that this arises as part of the solution, and it does. So what's really happening here is the real part of our root, the a, is still giving us the exponential part of our solution. But since we don't have repeated roots, we're not just putting on different power functions. We have complex roots, and what happens is you get two different trig functions to use instead as to define the two parts. So this is just what it is. Again, for further explanation, we can talk more about this in one-on-one meetings. But for our purposes in our class, this is really all we need to observe. And this simple example helps us at least see partially where this is coming from. So now let's go back to our original problem, which was a little more complicated because it didn't have complex roots that were simple like this example where a is 0. In this other example, a is not 0. So this was the example we considered first. Again, we look at the characteristic equation, plug it into quadratic formula, and I see there's a little typo here. There should be an equals, R2 equals -1 minus 3i. So we can just make note of that for now. But when you simplify those calculations, this is what you get. So our A is -1 and our B is 3. So remember, this is a plus or minus we get in the second term. So we really just want to identify what's on the other side of that plus or minus, and it's 3. So from our general solution, we put -1 in our exponential, e to the -1 times x, and then we introduce our constants c1 and c2 to add the trig functions, and inside the trig functions we put our b, which is 3 in this case. As an exercise, what you should do is just go and confirm. Take this function. If you want to put specific numbers in for c1 and c2, feel free. It doesn't matter. It'll work no matter what they are. Compute the derivative and second derivative of this function y and plug it into this expression, and you'll see that everything cancels out and you end up with 0. So this general form does work. So for that, we'll leave it at that, and in the last video what I'm going to do is I'm going to go through one example of each type of second order equation, one with 2 real roots, one with 1 repeated real root, and one with complex roots, and we'll have initial conditions, so we'll have to actually determine the constants c1 and c2.